We can also find the domain of a function just by investigating the expression or the equation itself. In order to do that, we need to look at the expression we're given and find all restricted values. In example 6, we have a fairly complicated looking function, but we have a nice shortcut that we can use, which is the knowledge that there are no restricted values for polynomial functions. That is, there's no value for x that we could substitute into this equation that would break it. We wouldn't be dividing by 0 or performing any other operations that are mathematically invalid. We can plug any number into this function, and we would generate a real number as a result. So we can define our domain for this function as -infinity to infinity without doing any work, as long as we can recognize that we're dealing with a polynomial function. In example 7, now what we have is a polynomial divided by a polynomial, or a rational function. For rational functions, f of x divided by g of x, we do have a restriction that g of x, that expression in the denominator, cannot equal 0. This tells us that if we're dealing with a rational function, what we need to do is take that denominator, set it equal to 0, and find all values for x that make that equation true. We'll have to factor here using difference of squares to get x minus 4 times x plus 4 is equal to 0, and giving us two solutions, x equals -4 and x equals +4. Those are our restricted values. What we're saying is x cannot equal those two values. And now we need to represent that in interval notation form. If it's helpful, since we'll have to make another one of these disjoint intervals, we can represent this visually. What we're saying is that our function is equal to 0 at -4 and 4. So those are the values that we want to exclude. And we want intervals that represent all of these other highlighted regions. To do that, we'll write an interval from -infinity to -4 with a rounded parenthesis to make sure we're excluding -4. Union -4 to +4, union 4 to +infinity. So essentially what we've done is taken that interval from -infinity to infinity, and we've inserted two gaps, one at -4, one at +4, to show that those restricted values are not a part of the domain. In example 8, we have a square root function. And the same rule will apply here that will apply for all radical functions. With an even index. What we mean by that is the type of root that we have. This is a square root. So even though we don't write it, that's implied to be a 2. But if this was a 4, 6, 8, etc., any radical function with an even index, square root of f of x, that function inside the radical must be greater than or equal to 0. In this case, that means that -x minus 3 needs to be greater than or equal to 0. And notice, for the purpose of finding the domain, we're only concerned with what's under the radical. Any expression outside the radical has no bearing on this. To solve, we'll add 3 to both sides, and then we'll divide or multiply by -1, whichever way we want to think about that. which will flip the direction of our inequality symbol, giving us x is less than or equal to 3. So our domain would be negative infinity to positive 3. In example 9, we have a problem that looks very similar, but in this case it's a cube root, meaning we have a radical with an odd index. So for radical functions with an odd index, so 3, 5, 7, and so on, there are no restricted values. Meaning once we recognize that we're dealing with a radical function that has an odd index, in this case 3, we can just state that our domain is negative infinity to positive infinity without doing any work at all. Because keep in mind, if we take negative 2 times negative 2 times negative 2, that would give us negative 8, meaning that the cube root of negative 8 is negative 2. We can have negative values under a radical with an odd index, but if it's under a radical with an even index, that expression needs to be non-negative, greater than or equal to 0.